chemical bonds, an introduction, and some review. For this whole chapter, we're going to be working on bonding. So first, we're going to do a quick reminder of what ionic and covalent bonding is and the differences between them. Then we'll move on and do a little bit more with Lewis dot symbols. I introduced this in the very first week of class, but now we can go a little bit more in depth. Then we're going to do some more. We're going to increase in difficulty level as we go throughout the chapter. And then we'll get to more complicated ones that actually break some of the rules I lay out in the first ones. At that point, we'll have enough information to go on and talk about resonance structure and then bond strength and length. And that will wrap up this chapter. So first, let's do some review. The goal of bonding is to make each element have a stable valence shell. This is often done by making it fully filled, or in other words, giving it an octet. Although we'll see that there are many atoms that break this rule. It can accomplish a stable shell by either trading or sharing electrons. Here we will discuss the three types of bonding, although in this class we will mostly be focusing on the first two. In ionic bonding, the atoms trade electrons. This typically happens when you have a metal and a nonmetal together. Since one is close to an octet, and one may only have one or two electrons in its outside shell, it's most favorable to make ions from the atoms by trading the electrons. In covalent compounds, all atoms may be close to an octet, so instead of trading the electrons, they will share electrons in order to reach their octet. The last type is very interesting, however, we won't be discussing it in too great of detail in this class. This is metallic bonding. Metallic bonding is special because all of the electrons are delocalized. Because they don't belong to any particular atom, they are also able to be moved across the metal if electrons are added to one side. This is called being conductive and is responsible for all the great things that we can do with electricity. Now let's go into a bit more detail on the first two types. Before we go straight into the bonding, let's talk quickly about how we represent these atoms. We will be using Lewis dot structures. The symbol for the element that we're talking about goes on the inside, and then the valence, or outside shell electrons, are represented by dots that surround the element. You put these in pairs. When we want to represent a bond, we will typically do so with a line. Each line represents 2 electrons. Now let's talk about how the bonds are formed. Let's look at an example of ionic bonding. We will look at the formation of potassium iodide. Potassium has 1 electron in its outside shell. If we were to remove that one, it would have a full octet in the lower shell. Iodine has 7 electrons in its outside shell, so if we were to add an electron to its outside shell, it would have a full octet. Therefore, it is favorable for the 1 potassium electron to be transferred to the iodine shell. What do you think it is that holds the potassium and the iodine together after the trade of electrons? Give this a little bit of thought before coming to class, and we'll discuss it there. Let's look at magnesium fluoride now. Magnesium has 2 electrons in its outside shell, and fluorine has 7. So magnesium would like to give up 2 electrons. However, it can't give them both to fluorine, since fluorine only has room for 1 more electron. Therefore, the magnesium will need to bind to 2 fluorines so that it can give 1 electron to each. Giving the magnesium a +2 charge and each fluorine a -1 charge. Now let's talk about a trick for being able to make these compounds a little bit faster than having to draw them out and count how many electrons are moving to each place. You'll have to be a little bit careful about using this, as we'll see on the next slide, but it's a handy trick for the most part. If we know the typical charge that each ion takes, to figure out what combination they will be combined in, we can take the charge and move it to the base of the other. We need the overall compound to be neutral, and now we can calculate how the charges work to show how the trick works. Aluminum typically has a +3 charge. We now have 2 of them, which gives us a total of +6. We have 3 oxygens, each with a charge of -2, which gives us a total of -6. So +6 from aluminum, -6 from the oxygen, equals neutral overall, which is what we need for an ionic compound. Here's an example where blindly following the Criss-Cross trick can get you into trouble. Ionic compounds always need to be the lowest whole number ratios. Be sure to note that this is not true for covalently bonded compounds. If we follow the trick, like in the previous slide, we will get Mg2O2. While this does give us a neutral compound, it's not the lowest whole number ratio. And so we must reduce it down to MgO. Now let's move on to covalent bonding. In covalent bonding, the molecule will be sharing electron density to make the octet. We represent these using Lewis structures, as shown here. Notice the chlorines are each sharing one electron. Typically, instead of representing all the bonds with these shared dots, what we will do is use a line. Each line represents 2 electrons. Now let's think about what would happen if the atoms need more than 1 electron. How could something like oxygen, which has 6 electrons, get a full octet? Think about this before moving on to the next slide. Now let's look at something like carbon dioxide. Carbon only has 4 valence electrons, and so it would need to gain 4, or share 4. Oxygen has 6 electrons, so it needs to gain 2. This means that for everything to have a full octet, carbon needs to share 2 electrons with each oxygen, and then each oxygen will share 2 with carbon. We can draw this in 2 different ways. The first is to leave the dots for the electrons. This isn't the standard way of doing it though. We typically are going to replace these bonds, or these electrons, with lines representing bonds. Just like on the last slide, each line represents 2 electrons. This is as far into Lewis structure stuff as we're going to go right at this moment, and we'll get into much more detail as we finish up this chapter and especially in the next chapter.